Hey guys, so in this video we're gonna talk about how to integrate a function that is revolving around a Cartesian plane. Say if we have this two-dimensional graph and let's say if we have this kind of function and this function here which we call f of x, and by the way it looks like a square root of x, and this function here revolves around a kind of a circular shape, and this creates a volume of it. And note that the area of the circle is equal to pi r squared. That's the area of the circle. Now, how do we find the volume of this particular volume of this sphere here, or this shape? Now, note that actually I'm going to improve the drawing real quick because this looks unrealistic. Just trying to make it look pleasing. Go. Much better. Right. Now, remember that in a definite integral, if we have a point from a to b, this is a, this is b, and the definite integral is this. So the integral of, hold on, let's put in the center. So the definite integral state that big F of x is equal to the integral from point B to A f of x dx, where we are basically calculating the area under the curve of this rational function, sorry, of this radical function. So from point A to B, and this is our x, this is our y, so we are basically calculating the area under this curve. And note that I'm going to use a different color here. And note that in this case here, this small chunk of area under here, we call this d of x. And this length here is called the f of x, the small f of x. And note that we can establish this as a very, very small incremental size of rectangles. That's basically what integrals or definite integrals are made up for. A very precise small rectangles that are fitted in this graph here under the curve. So in terms of defining or looking for the volume under this thing here, we are going to use this method called disk or washer methods. Now note that in this particular theorem, this length from here to here is an f of x, and this width from here to here is our d of x. If we are going to multiply the f of x from here and the d of x from here, we're gonna have, or we are going to obtain an area under the curve, which is what this definite integral looks like, the big f of x, or a, the area under the curve. But in this case here, if we come look at this context here, this basically means that we are kind of revolving this function here, or this radical function, and that we can say that our radius is f of x. So our radius is f of x, which is the square root of x. Sorry, yeah, the square root of x. And if we are going to revolve that, which is what's going on here right now, we can figure out the volume of this small disk over here. Now, to graphically understand this, we are taking this small portion of this shape over here into some kind of like a shape of a cylindrical structure. But sorry about that. But in this case here, this line over here is not constant, not straight, and we are only taking the partial amount of the volume here. So say this is our part A and part B, and that right here is our radius, or I guess you can say our f of x. And by the way, as I said here, f of x is the radius. Okay, now to find the volume under the curve, note that the integral, note that the area of the circle is now called pi r squared. In this case, we just noted that r, or the radius, is the function itself. Now it is called f of x squared. Cool. Now, if we are going to integrate the area, or this particular area, we are gonna have the volume of the disk, which is the integral from point B to A pi times f of x squared times dx. And in this case here, our dx is the small incremental size of width from here to here. Okay, I'm gonna make some examples here. Just note that this one here is the equation of finding the volume under a disk. Okay, say if we are going to find the volume under this curve here, and right here is our radius here, from point 1 to point 3. In this case here, the equation is gonna be volume is equal to pi times the integral of from 3 to 1 squared of f of x dx. In this case here, our f of x is actually 5x, so we can substitute that from there, which will give us 5x squared. Actually, that will give us 25x squared. So that's gonna be 25x squared dx. Now, see, if we are going to integrate that, we're gonna have pi times 25x squared is gonna be 25x cubed over 3, and from 3 to 1. And if we are going to substitute everything, we're gonna have pi 25 times 3 cube minus 3, over 3 minus 25 cube over 3, which will gives us, and I'm actually gonna use the calculator for this to crunch up some numbers. So 25 times 3 cube over 3 minus 25 1 cube over 3 times pi, which gives us approximately 680.68 units cube. So this right here is the volume of this area under, of this volume under the curve. And the volume, if we are going to systematically graph it, it's going to look like this. Where this from 3 to 1, and we are basically And we are basically going to be calculating the volume under this curve here.